Hey guys, in the previous video we saw another type of elementary flow called the source and sink flow, and then we put together a uniform flow, a source and a sink flow, and what we got as a result is called the Rankine's flow. Today we will be looking at another type of flow, which is a variation of a combination of source and sink. It's a very important flow because we will be using this flow in the subsequent videos as well. This flow is called the doublet flow. In a doublet flow, we use one source of some strength, let's say lambda, and one sink of strength minus lambda. So we have a source and we have a sink, and the separation distance, let it be called L. Now in a doublet flow, what we are trying to do is that we are trying to bring the source and the sink very close to each other, and we are trying to basically achieve the flow over a cylinder, keeping in mind the kind of flow we had in the Rankine's oval. Given the separation between the source and the sink, we got a flow around an oval. Now we are hoping that as we bring these two close to each other, both close to the origin, the oval will become a circle. Unfortunately, the issue, as you might have already realized, is that if we put the source and sink both at the origin, it's not going to create flow over a cylinder. Rather, the source and the sink will just cancel out each other's effect. So just bringing them both to the origin does not make sense. We need to have some sort of a constraint which will make sure that these two don't cancel out each other's effects, and that condition is important in the derivation of doublet flow. That condition is that lambda L, which is the strength of the doublet times the distance of, the strength of the source or sink times the distance of separation between the source and sink, has to be a constant. So given this constraint, we will try to understand how the doublet flows, stream function or velocity potential function, etc., can be derived, right? So now we know that the stream function for a source flow, let's just write that down here. We know that the stream function for a source flow is given by lambda by 2 pi theta, right? So if I have a point xy in the flow field, then the stream function at this point is going to be dictated by the sum of stream function due to the source plus the stream function due to the sink. So if I join these 2 points, and if this angle is theta 1 and this angle is theta 2, then my stream function at the point P would be, using the same result, lambda by 2 pi into theta 1 from the source and minus lambda by 2 pi into theta 2 from the sink. That gives me lambda by 2 pi theta 1 minus theta 2. As you might have imagined, what we are trying to do here is we are trying to bring the source and the sink close to each other such that L goes to 0. So in that case, what happens is this theta 1 minus theta 2 will become a very small quantity. So if you look at this figure, theta 2 is the exterior angle of this triangle. Let me name the triangle ABP, right? So the sum of this angle and theta 1 is going to give us theta 2, because theta 2 forms an exterior angle. So this angle, let me call it delta theta, is going to be equal to theta 2 minus theta 1, right? So now I can just plug in delta theta here. So this is going to be equal to minus lambda by 2 pi delta theta. Now let's just write this result down here and erase the rest of the board. So I have stream function is equal to minus lambda by 2 pi into delta theta. Now let's say that I have brought these 2 points, the source and the sink points, very very close to each other, both close to the origin, such that L goes to 0. So let's try to find what expression we need to substitute in this equation for delta theta from this figure. So for this, let me just isolate the triangle out for clarity. So yeah, that might not really be appropriate. What we will have is a long slender triangle with this angle being delta theta. Let me call this angle theta, right? Let me call this point P, point A, point B. AB is the distance of separation between the source and the sink. So let me call that L. Let me call this side AP as R, BP. Let me call this B, and if I drop a perpendicular from B to the opposite side P, let's say it meets that side at the point, what haven't I used, C, and let's say the length of this side BC is A, right? So now we have 3 triangles which we will be using. What are the triangles? ABC is one, ABC, BCP, and of course the big one, ABP. First of all, from triangle BCP, we can say that sine of delta theta is equal to A by B. Now, as I said, as L approaches 0, the delta theta, the value of delta theta is going to be very very small, again very close to 0, and for very small angles it's a very well known result that sine theta, for theta being very small angles, is almost equal to theta. Hence here we apply the same approximation and we say that sine delta theta is almost equal to delta theta, which is almost A by B, right? Now we've got delta theta in terms of A and B, but that's not sufficient. We need to get A and B now in terms of L, because for us what's important is we need to get L into the expression psi for psi, because we need to satisfy this constraint that lambda L is a constant for the doublet flow. So let's try and now express A and B in terms of L. So now from the figure triangle ABC, we can say that L sine theta is equal to A, right? So A is L sine theta. Now let's look at the side AP, right? Let's say side AP. What is AP? The distance of AP, the length of side AP is R. So R is equal to AP. Now AP can be broken into two lengths, AC and CP, right? So now what is AC? AC from the triangle ABC is L cos theta, right? This is AC and this is L and that's theta. So AC is L cos theta plus CP. CP comes from the triangle BCP and can be written in terms of B as B cos of delta theta. And now we apply the approximation for delta theta being very small. For very small angles, like how sine theta is close to theta, cos theta will be close to 1. And hence we apply that approximation here for delta theta and get the result that R is equal to L cos theta plus B, right? And from here B is equal to R minus L cos theta. So we have two expressions, A in terms of L and B in terms of R and L. Now let's substitute these two expressions back into the expression for delta theta. So what we get is delta theta is equal to A by B, A being L sine theta and B being R minus L cos theta, right? So now let's substitute this expression back into the expression for the stream function. So what we get is psi is equal to minus lambda L sine theta divided by 2 pi into R minus L cos theta, right? So now we apply the limit. The limit, let me just clear this board. So now we apply the limit of the stream function as L approaches 0 while keeping lambda L a constant. Let me, as per convention, call this constant kappa. So now on applying the limit, what we get is limit L tending to 0 lambda L is equal to kappa minus lambda L sine theta by 2 pi R minus L cos theta. So because of the constraint, this quantity lambda L is going to just be a constant kappa. So I can remove that out of the limit. Sine theta is not affected by the limit by 2 pi, which is a constant, and applying the limit L tends to 0 makes this quantity 0, and what I get is minus kappa sine theta by 2 pi R, and this is the stream function for a doublet flow. Now one may perform a similar analysis for finding the velocity potential, but the easier way perhaps is that you differentiate the stream function to get the velocity components, and then using the velocity components you again try to find the velocity potential by integration. Now let's just see how these streamlines would look. Now for that I might have to convert this expression from the given polar coordinates to a Cartesian coordinate system, just for the sake of simplicity of plotting. So what we have is minus kappa sine theta by 2 pi r, right? So let me now use the relations between the Cartesian and the polar coordinate system for performing the transformation. So the relations are y is r sine theta and x is r cos theta. So now from here the stream function can be written as minus kappa sine theta from here is y by r, so that makes it r square. Now that is kappa y by 2 pi, r squared can be written as x squared plus y squared. So if I am plotting the streamlines, I need to basically plot a family of curves such that psi is a constant. So let me just put this expression equal to a constant, and as I vary the value of the constant, I am going to get a family of curves which will denote the streamlines of the flow. So let me put this is equal to a constant, right? So I can combine this and call it a single constant, maybe a capital M. So what I get is x squared plus y squared minus my or plus my, doesn't matter, is equal to 0. So from here I can just complete the squares, right? So what I can do is I can write this as x squared plus y minus m by 2 the whole squared minus m squared by 4. I hope that's right. So y squared comes from here plus m squared by 4 minus m squared by 4 gets cancelled, 2my by 2, so that's my. So this is right. So what we get now is x squared plus y minus m by 2 the whole squared is equal to m squared by 4. So this is clearly an equation of a circle. And what are the properties of the circle? Where is it centered? It's clearly centered at x equal to 0, which means it's the y-axis. And I'm sorry, it's centered at x equal to 0, yeah, which is the y-axis, and it's centered at y equal to m by 2, the radius being m by 2. So if I had to plot this, the center would lie somewhere on the y-axis. The circle passes through the origin. As you can see, if I set x and y to be 0, it satisfies the equation m squared by 4 equals m squared by 4. Hence what I will get is a circle that passes through the origin centered at this point 0 comma m by 2 and of radius m by 2. So as I vary the value of m, I will essentially get different circles, all of which pass through the origin. So this is how the streamlines of a doublet flow look. Another thing is the doublet flow is typically associated with a sign, and the sign points from the source to the sink. So as you remember, when we started the derivation, we had a source to the left and a sink to the right. So the doublet flow, as per convention, has a direction from the sink to the source. So on the streamlines, if I had to put arrows, I would have a left facing arrow right at that point, and the rest of it would look like this, as though the streamlines were emanating from the source, going around and collapsing back into the sink. So this is how the sign convention for the doublet flow is. One more thing that I would like to point out before I wrap up is that you can still ask the question, so on bringing the source and sink together, satisfying this constraint, no matter what constraint you use, how is this helping us avoid cancellation of the source and the sink? That's a question that you may ask. So the reason for that is it's a purely mathematical explanation. So when I say that the distance L goes to 0 and this quantity has to be constant, what I essentially mean is, as L goes to 0, in order to keep this value a constant, the lambda has to be infinite, right? So let me just explain that here. So I have lambda L equal to constant. So how does this constraint help? So as L tends to 0, in order to keep the product constant, my lambda has to go to infinity. And when you have something like infinity, you cannot cancel them out. So you have the infinity from the source and you have infinity from the sink. And you cannot say infinity minus infinity is 0. You cannot say that, because it becomes an expression which cannot be evaluated. So that becomes an indeterminate quantity. Hence we have used this to exploit, and we've tried to use this constraint in order to build a flow which is called the doublet flow. So I hope the contents of the video were clear. If you have any doubts, please feel free to contact me. You can also drop comments below. In the next video, we will try to put together a doublet flow and a uniform flow and see what we get. And that's about it. See you in the next video. Thank you.